Amelia and for Joey and for Greg. All right. First, we welcome Dylan. It's so good to have you back. So good to have you back. Okay. This really would be our target question of the day. Really. Which is the most reactive element and why? And which is non-reactive, but why? So we may look at that and say, oh, who cares? That really ultimately is the power of the periodic table. Where an element is located, we can predict how it will behave in a chemical reaction to satisfy different needs. So we will be able to answer that at the end of our time today. So if we are turning to any specific place in our packet, it would be focused on our periodic trends. Okay, so before we revisit size, what I'd like to do, keeping in mind Coulomb's law, to kind of sketch out on the periodic table, as we proceed down a column and then proceed from left to right across the period, or I should say group or family, how do we know the structure changes? All right. Not required to write anything down if you want to sketch, but I thought that it would be worthwhile to quickly just remind us. So we know this is the S block. The first position of the S block, we are filling S1. However, we're going to different energy levels as we go downward. All right. So if I want to kind of just lamely draw the electron cloud as a circle, but we know it's not a circle, it's fuzzy, but just for discussion's sake. So these elements, are in the first energy level, and then these will have the first energy level, but then also the second energy level. These will have the first, the second, and the third, and on and on and on and on. Yeah? All right. How about across the period? So if we want to use the fourth period, if you don't mind, as our main example. So we're filling the 4s, then we know we enter the D block, and that will be 3D. So officially, the electrons are assigned to the fourth level, but then we go into the third level and then come back to the fourth. So as we go across, yeah, we go a little bit into the third, but it's the fourth level. Oh gosh, I should have drawn this. You get the ignore that outer one. So that's the energy levels. That's D. The distance the electrons are from the nucleus. But is our nucleus changing? And as far as changing, why did you go thumb up? More protons. So now we know that the nucleus is incredibly small, but just to picture that, is it okay if I, one single proton, but then by golly, francium 87. So I'm going to make that bigger to just reference, of course, not the size of the nucleus, but the Q value. Yeah. So as we go downward, the nuclei, we're adding more protons. So as we proceed down, D is increasing. Yeah. Now, again, I know we could call this R, but I'm going to always call it D, the distance between our ion centers, which would be the nucleus or charged species to the electron on the outside. But we know that Q is going up as far as the protons. Is that all right? All right. How about across a period? D increase, decrease, stay the same. So if we're doing the fourth, adding electrons to the fourth, go into the 3, 4th. Same-ish, yeah? Not like when we're going down a column. So there's no change in the distance. But as we go across, with every move to the right, Q is increasing. Because we're adding another proton, another proton, another proton. Okay, is that all right? I did a much better job. So there's our just blocks of the periodic table. And then here's a little better. You know, I'm so challenged artistically. But to show, holy smokes, additional layers here, no, same amount. But if we're trying to picture Q, our number of protons relatively as the size of the shaded in green, it's getting bigger, but it's in both directions. Good? Okay. So we go back here. We get larger as we go down a group, but we get smaller as we go across. Why? Take it away, sir. Hold on one second. What direction are you going? Are you going? I apologize very much.
As it goes,
So across a period, the Q, so the number of protons. Now, there can be another way we represent protons. A way that we can write an element, of course, is its element symbol. But there's something called the nuclide symbol. And the nuclide symbol has your element and then a subscript and a superscript to the left. And the subscript is the atomic number of protons. And the superscript is the mass number. And then if you have a charge, a positive or a negative, 0, if it's neutral, you don't see it. But if there is a charge, it'll be shown there. For example, oxygen, if we're dealing with the most abundant form, 8, 16. And then if we're dealing with the ion, it's -2. Is that all right? Where someone along the way gave a special letter designation for atomic number. They call it Z. I don't know why. And if we're doing the nuclide symbol, we'll sometimes call the mass number A. All right. So this Z is referred to as nuclear strength or nuclear charge. It's the number of protons. The greater the number of protons, the more positive, the stronger the electrostatic pull. So as we go across the period, Q is increasing, number of protons, or we could say Z is increasing. Yeah. Okay. Is it all right if I add a little other layer to this? Whenever we are talking about size, like if we talk about the 4th period, we realize, for example, potassium has a nuclear strength of 19. And when we're talking about size, we're talking about the pull this has for the 4th energy level electron. Well, the nucleus, yes, has a certain attraction based upon the distance and then how many protons and electron.
but there's also electrons leading up to that that are taking some of the electrostatic force. That concept is called shielding. It is not a priority. It is not a priority, no matter what we see. But we just say like, the pull of the nucleus is a little lessened because we have other electrons that the nucleus is interacting with before we get to that electron. Yeah? So kind of like, I don't know, you're working your way through a crowd to find your sweethearts. You just can't wait to hold them close, but you got to work your way through the crowd. So by the time you reach them, a little bit of your effort has been exerted. Kind of the same thing. Joe, are you thinking like, not me? I'm just going to bound over those. All right. So because of that, we put a little EFF. It's the effective nuclear charge. It's just acknowledging that, okay, we have electrons in the way. So it's not going to be as full of a force as if they weren't there. Okay, so it's called effective nuclear charge. Bless you. So I feel it's my job to show us best, but also to expose us to like the different kind of ways that could be represented symbolically. So we could say going across a period, the Q value increases. We could say the number of protons increases, the nuclear strength increases, or ZEFF increases. Any of those is sufficient. Okay, can you go ahead and take over from here? So the strength of the nuclear pull is increasing.
So the electrons are pulled closer to the.
Why?
There's more protons. Like
You're so correct. You are so correct. However, right, going down, there's more protons, but the atom gets larger as we go down. So what's the other part that we need to address? So we address the numerator. What's going on with our denominator? As we go across a period, is the distance of those electrons changing? No. So, and electrons placed in same, pretty much, D. Okay, so this is kind of the claim. Yeah, atomic size is decreasing. This is the evidence. So then what's the reasoning? It's going down because we're adding more protons. The electrons are placed the same distance. Therefore, electronegativity, the pull a nucleus has for electrons in a bond. So is it okay that we reserve that term? So would it be okay if we replace more electronegative with the force of attraction of the nuclei for the electrons increases, which results in the atomic size decreasing? Is that all right? Now, you know, you never have to have exactly what I have. So you could have modified that. Absolutely. Concerns. All right. So then what is going on as we go down? We're getting larger. So Coulomb's law. What's going on with the Q? As we go down, hydrogen 1, lithium 3, sodium 11, more protons. So Q is increasing, or we could say ZEFF is increasing. more protons, nuclear strength increases. But D is increasing. We are adding energy levels, not just sub-levels. We're not just adding, more to a relatively the same distance. We're adding a whole new layer or a whole new shell. We want to think three-dimensionally, of course. So even though we are beefing up that nucleus, the distance that makes the greater impact. Okay, so adding electrons further away, therefore, the force of attraction of nuclei for electrons is decreased due to increased distance, which equals larger atomic size. Very, very rarely will we be given a list of elements and just have to rank them in order of size based upon location. We're going to have to justify. Questions for me? All right. There's 4 periodic trends we usually address. One that Jacob recalled is in chapter 8, electronegativity. That's chapter 8 for us. So we, in this chapter, per Zumdahl, are going over atomic size, ionization energy, and electron affinity. These are the big ones that we have to be able to justify, because it's because of these that so many chemical behaviors are. So if there's a most important, it would be these. Okay? So we have to know electron affinity, but it's just not, I don't know, as core of a concept. So the deal is ionization energy. Oh, I wish we called it something different, because I think we just think, well, we're making an ion. Well, a cation or an anion. Electronegativity is the energy required, so it's invested, to remove an electron from a neutral atom or ion. Elena, could you choose any element? Excellent. So if we are coming up with the equation that represents ionization energy, sodium has its nuclei and its electrons up to the 3rd energy level. Okay, the closer an electron is to the nucleus, the lower in energy it is. We are trying to remove one, remove it. So to do that, we have to invest energy to kick it out, because it's being held by the nucleus. There's a force of attraction. Yeah, and based upon the strength of the nucleus and how far those electrons are, the ionization energy is what we're adding to overcome that. Remember, in the PES spectrums, the binding energy. So I could call it E, or I could call it IE. And then, Robert, if we remove an electron from sodium, what do we form? You got it. So we're forming cations. We're forming cations. Okay, now, truly, Elena could have chosen any element, any element. What if, Elena, you gave a non-metal? Do you mind? Oh. And we may say, wait, but nitrogen, it's a non-metal. If given the chance, it's going to form an anion. Sure, but we're not giving it the chance. We are investing energy to remove the electron. And we don't want to treat it like it's a human being and say, but it doesn't want to get, we're investing the energy. It has no emotions tied to it. Same like noble gas. If we invest enough energy, yeah, we're kicking out an electron. So no, do we say, oh, but it doesn't want to? There's no emotion, okay? So you can remove electrons from any element. Can we go to our pink packet, please? All right, and page 3, please. Page 3. Okay, so same information, just being conveyed a little differently. What we're seeing here are just our main group elements, the S and the P block, yeah? So let's go down the column. What happens to ionization energies as we go down? Buff. It decreases. So ionization energies decrease down a group. Why? We are removing electrons further from the nucleus. Why does it require less energy, Justin? Yep. So just think, holding your sweetheart nice and close versus holding them barely hanging on. You know, the further barely hanging on, so much easier to remove than holding nice and close. Coulomb's law. Okay, as we go from left to right, it increases. We know across a period, D is not changing, you know, relatively, not changing enough. But our nuclear strength is increasing. So the force of attraction as you move left to right is increasing. So therefore, the energy required to remove electrons increases. Oh, force of attraction, 4 electrons of 4 electrons. Good. We're going to come back to this. Could we just turn the page, please? We can keep removing consecutive electrons. So this is a table showing us I1, first ionization energy, meaning we're removing the first electron. So we're forming a +1 cation. The second, we're removing the second after we've removed the first, creating a +2 out of a +1, and so on, and so on, and so on, and so on. Does it make sense that as we move to left to right, our numbers increase? As you remove consecutive electrons, more energy is required to remove electrons. Sodium, 11 protons. The first ionization energy removes the 3s1. The second ionization energy removes one of the 2p. And then another 2p, and so on and so on and so on. So as we remove consecutive electrons, two things are happening possibly. We are removing them physically from a closer energy level, but also our nucleus is not changing. Oh, sugar. That's the secondary. If we are changing by a whole energy level or a sublevel, the smaller the denominator, the larger the force of attraction. So it should get consecutively greater and harder to remove electrons because we're removing them closer from the nucleus. As we're removing electrons, not because we're adding protons, but because we're removing electrons, we are, in essence, increasing effective nuclear charge, but that is pulling them closer to each other. So therefore, it's really the distance overall that we have to address. Okay. But then as you go from left to right, there are big jumps in value. That's what this staircase is showing us. Alan, could you choose any of the elements from silicon down? Sounds good. It relatively usually doubles or triples as you remove consecutive electrons. So that's about doubling. About doubling. Kind of doubling. But often we get to a point where there is a huge jump. It is like 10 times. Magnesium, okay, 738 to remove the first, 1451 to remove the second. Whoa! It's like a 7-fold increase, 6-fold increase. Why is the third ionization energy so much higher for magnesium? Go. So
it's now energy level.
I am so proud of your answer. You feeling chocolate today or Smartie? Fruit juice.
Smart.
That is a 4 Smartie answer. Yeah. Can I just tell you why so much? I'm gonna say, well, when you remove 2, the octet is there. Does sodium know? Does sodium even know that we humans have made up this octet thing? No! Oh, let's reach the noble gas configuration. Does sodium know what a noble gas is? No! So we talk about structure, not like all of a sudden emotions come out. Okay. We talk false. All right. Could I ask us, let's go ahead and just apply some of this stuff. So page 1, could I ask you to answer? We haven't, it's not talking about electron affinity. Oh, it is, crud. Okay, could you answer 1, 2, and 4? 1, 2, and 4. One nice warm up, not periodic. Where are the elements that I'm asked? Well, first, it's beryllium, boron, carbon, nitrogen. We know we get smaller, but we're talking about neighbors. Then we have carbon, phosphorus, selenium, iodine. Oh, diagonal. Then we have neon, argon, krypton, xenon. Now that, because we're talking about a whole nother layer. So that is definitely out. No. Chromium, magnesium, iron, cobalt. Oh, well, isn't that similar to this? Now, of course, here you're going right from S to P. Here we're staying within the same D. So maybe these would be a stronger choice over that. Magnesium, calcium, strong. Oh my gosh, no, because that's talking about down. So, what is better? Next door, diagonal. We get larger, we get smaller. We get larger, we get smaller. We get larger, we get smaller. On a diagonal, they're on average close in size. So that is carbon, phosphorus, yep, D. Questions? Yesterday I saw a comic that had a book that width and a book that width. And it said chemistry including exceptions. The more and more and more we learn about chemistry, the more gray there is. I really appreciate that we've been relieved from knowing exceptions. We don't have to memorize them, but if an exception is brought to your attention, we need to be able to explain it. Okay, if we could go back to, I said we'll go back to this page 3. All right. Whenever we talk about trends, we're talking about generalities. Generalities. So can we see from lithium to neon, that's across a period. Sodium to argon, across the period. And we know across the period that we're increasing. Across the period. So I'm just drawing a linear line because that's what we anticipate. But it's not linear. It's like a set of mountain peaks. There are some that have a lower ionization energy than we would expect. And there's some that have a greater than we would expect. We don't have to know the exceptions. We just have to explain why. Okay, so Dylan, yellow or blue? Yeah, just pick. Oh, of course, blue. Right, Brendan? Pitt. Just kidding. So, what is that? That's zinc. Zinc is argon, 4s2, 3d10. So what this is telling us, if we would, draw sugar, but that is a higher value than we would anticipate. Where right next door, gallium, whoa, look, it is much less than we would anticipate. Why is this lower than we would expect? So what that means is the ionization value is less than we would predict. We're here, wait, no. The ionization energy experimental is greater than the theoretical. I'm sorry. Here, the ionization energy experimental is less, actually much less than theoretical for gallium versus zinc. Why? Go. Why? You are absolutely correct. So removing the 4p1 electron from gallium, requires less energy than expected, because what, can you repeat what you said? You're right. It's not paired. Why do we fill the 4p after the 3d, Gabby? It takes more. What do you mean it takes more energy? No problem. No problem. So that whole off-ball chart thing.
Yeah.
We follow the arrows. Why do we fill 1s and then 2s and then 2, like what, why? How does 1s compare to 7s? Way closer to the nucleus, way further from the nucleus. So what's true about these electrons versus those? Okay, so you are absolutely correct. Full. It is a different sublevel, and we fill it after the 3D. So yeah, the force of attraction for 4p is less than the force of attraction of the 4s and the 3d, because 4p electrons must spend some time further from the nucleus. Otherwise, we wouldn't fill it after those two. 4p greater d. Okay, so here, 4s for zinc filled, 3d filled. I am very crazily keeping them into homeroom. I very well know this, but I know they don't want to stop learning chemistry. I just need to finish this one thing. You definitely can. Okay, I'll see you third. How nice. How polite. I appreciate that very much. Anyway, okay. We're being told it takes more. So we are removing one from a complete shell. No, it's not that. It knows it's complete. It's higher, so it must be greater effort, because we are removing an electron from the full shell. So it requires more energy than we would predict. Okay, I just wanted to address that. Electron affinity, super not bad. Please, please, please work on a chunk of the unit assignment over the weekend. All right, we will test Wednesday. Monday, we're just going to problem solve. First, address any of your questions, but then problem solve. I'm so sorry I went into homeroom and cut from the announcements. If you have any questions, please let me know.